Okay, guys, so we're going to take a look at some of the material in Chapter 1, Introduction, Measurements, and Estimating. Okay, so let's get started on, oh, well, let me full screen this. So let's get started here on this. Okay, so here's what we'll learn in this chapter. Measurement and uncertainty, significant figures, SI units and unit conversions, scientific notation, and dimensions, and this thing called, excuse me, dimensional analysis. Now, this stuff will appear quite easy and simple for you if you've already seen this in another science class, but for those of you who haven't, it's kind of important and you want to learn this early in the semester so you have a good start. Let's talk a little bit about the scientific method, which is kind of covered in this chapter, but not quite in a complete kind of picture way. The scientific method begins by making observations, which basically means to notice some patterns in nature. And sometimes the patterns are easy to see, and sometimes they're quite a bit difficult. Once you've made some observations and you kind of identified a pattern, you hypothesize or write down a hypothesis, which is an attempt to explain the pattern. You're going to try and use that hypothesis to predict other patterns. Like, for example, if you're a biologist and you take a look at flower petals, for example, you might have a prediction on how those flower petals are laid out on those flowers by making some observations. You write down your hypothesis, and then you take it upon yourself to observe as many of those kinds of flowers as you possibly can to see if that matches that hypothesis. Once you've done that, that's kind of the testing period, which is where you do experiments. In a physics setting, it would be experiments, or further observations, which might be like looking at patterns of flower petals. And you use those observations to determine how correct your hypothesis is. Now, your hypothesis might be pretty good, and you just need to modify it a little bit. And so that's kind of why I've put correctness in quotes there. So you can modify that hypothesis and make it better. And once you've done that a few times and you go through that iterative process of refining your hypothesis, eventually that hypothesis is elevated to the status of theory. Now, a scientific theory is often different than our everyday use of the word theory. What a scientific theory is it explains a very broad set of observations, and it can be used to make predictions about patterns that have not yet been observed. So, for example, like you might, with the example of the flower petals, right? You might start observing a certain type of flower, make a hypothesis, take more observations and see that, wow, this is a good hypothesis, and try to apply that hypothesis to other flowers. And you might find that, yes, flowers which are kind of not the same flower, but maybe related to that other flower, also follow that same pattern of observation. And then you're kind of right there. You've got yourself a theory there, right? Okay. Any questions about that scientific method, or is this kind of stuff most of us understand? Okay, no questions. We'll go ahead and keep going. How does a new theory become accepted? Well, it's kind of that process of testing it many times over. The beauty of science is that you could be in California here with us, and somebody over in Russia, for example, could look at similar flowers and verify that hypothesis, or verify or improve upon that hypothesis, right? And so it's a collaborative effort, and your hypothesis cannot just be something that works in California, right? It has to be something that works everywhere in order to be elevated to this level of a theory and become accepted in the scientific community. So your predictions have to agree with the data and the observations, and you have to explain a wide range of phenomena. Okay, that's what a theory is. Now here we have on the left kind of an Earth-centric model of the solar system, and I believe we have some zodiac signs sprinkled in there as well. Now that is not a theory. That is not accepted in the scientific community. Nothing to do with zodiac or flat Earth or um, Earth-centric models of the solar system are accepted in the scientific community because the evidence is just not there. We have an alarming amount of evidence for the picture on the right, which is not a very modern picture, but it is the heliocentric model of the solar system, first hypothesized by Copernicus. Copernicus was a religious man involved in the dealings of the church, during times of the Dark Ages. Certain inquisitions and things might have been going on, and so um, I believe he didn't publish his results until towards the end of his life, even though he knew that the sun was at the center of the solar system for quite a long time. And so you kind of get this idea from this picture that the planets are moving around the sun in these perfect circles. Now, that is not true. We understand now that the orbits of the planets are elliptical. They are ellipses, not circles. So even that picture on the right is not fully correct, but it's a much better picture than the one on the left. Okay. Why should we study physics? Well, maybe you shouldn't study physics. Maybe physics is not right for you, and you can go about your life happily ever after, right? But maybe physics is something you should study, and we should understand physics kind of as at the societal level, right? It should be a baseline level of understanding that everybody understands a little bit of physics, so that things like this don't happen, right? There's a lot of stuff that goes on in modern, engineering practices, right? Things are double, triple, quadruple checked all the time, but still incidents like this can happen, right? And so the more people that are familiar with these kinds of physics principles and calculations and things, the less likely it is that something like this on the right can actually happen, okay? Now let's get away from, kind of the general science stuff and kind of get into measurements here, the actual hard science. Okay. No measurement is exact. That's a very important thing. It doesn't matter what field of science you're in, no measurement is going to be exact, right? And oftentimes we have to resort to statistical arguments or results which have error bars, right? Uncertainty in the measurement, which we'll also talk about here. And that is another key point, is that uncertainty is always there, no matter what you do. You cannot get rid of the uncertainty. So for example, here we have like a little piece of 2x4, and we're measuring the length there, or rather the width of that 2x4. And if I just eyeball it here myself, it looks like 8.9, 8.8 centimeters, something along those lines, right? I'm sure you guys can agree if you take a closer look there. And so we would write that measurement down in the following way, okay? We would say the 8.8 is the actual measurement that we took. That's the value that we see when we look at the ruler. And of course, that's not perfect. And so we add this piece here, the uncertainty. Now, when I look at this ruler, I said, okay, this could be 8.8 or it could be 8.9. And so one might agree with the following statement. The uncertainty in the measurement is 0.1 centimeters, right? Now, that's an uncertainty, meaning that the value of this measurement could have an entire range of values between, let's say, and this is not mathematically accurate what I'm about to say, but it gives you an idea. The range of allowed measurements here for this 2x4 for the width is somewhere between 8.7 centimeters and 8.9 centimeters. That's not mathematically rigorous, that statement, but that gives you an idea of what uncertainty means. Okay. Does anybody have any questions about that? Okay, so we'll go ahead and keep moving. We like to write our measurements like this, with this plus or minus 0.1 centimeter. We call that the estimated uncertainty. Sometimes we call it the sometimes we call that what do we call it? The resolution of the measuring device. Sorry about that. That uncertainty there is related to the resolution of the measuring device. So if you have a better ruler, that number would be smaller, right? If you have a worse ruler, that number would be larger. Okay. In addition to this idea here of this plus or minus zero point 0.1 centimeter, we also have the idea of a percent uncertainty, right? And hopefully this is not too big of a jump from what we've just shown. Percentage, right? You take the actual estimated uncertainty and just divide by the value that you actually measured, the 8.8, then multiply by 100%, right? Standard percentage calculation. And this calculation rounds off to about 1% uncertainty there. So 1% uncertainty in our measurement, that seems like a pretty good uncertainty. But you can never be too sure, right? Sometimes you really do need a high precision measurement, and 1% uncertainty is very, very big in some cases, okay? So for example, the Golden Gate Bridge is a very long bridge, right? 1% uncertainty would be way too much uncertainty, right? You would really want 0.0001% uncertainty just to be safe, right? Make sure everybody's going to be safe driving across that bridge. Okay, that brings us to this idea of significant figures. Significant figures is basically the number of reliably known digits in a number. So let's take a look at this number that we already have here. This is the measurement that we took of that little 2x4, the 8.8 plus or minus 0.1 centimeters. Now, how many significant figures do we have here? Well, we have 2. Let me explain. This is the number that you want to look at when dealing with significant figures, okay? That 8.8, the actual number that you read off of your ruler. The uncertainty has nothing to do with the significant figures of the measurement. It has to do with the error of the measurement, right? And so we have 2 significant figures here because we've written this number as 8.8. Now we could make this number more accurate artificially. If we had a better ruler, we could say this is 8.8000, meaning we know the digits that come after the 8 are zeros, in which case we better have less uncertainty, right? So a number that has zeros after the decimal is more accurate than a number that does not have zeros after that digit there, after that 0.8. If you have more zeros, more accurate. If you have nothing after that 0.8, well then you're at 2 significant figures, okay? All right, so here's an example of another number. Now this number doesn't have zeros after that 2 at the end, it has zeros before. This is an example of a number which we've presented as a 4-digit number, but in reality, this is not a 4-digit level of accuracy. This is only 2 digits of accuracy. This is a 2 significant figure measurement, okay? The initial zeros don't count because we could have used, like for example, this measurement here could be kilometers, right? And so we used a meter stick to measure 62. If this is kilometers, then the 62 there is 6.2 centimeters, okay? And so, excuse me, if this, I messed up. Back up a second. If this number is measured in meters, excuse me, not kilometers, if it's measured in meters, then this number is 6.2 centimeters. Now, they're giving this value to us as 0.062 centimeters, okay? But if this was measured using a meters stick and measured in meters, it would be 6.2 centimeters. Does that make sense? That it's only going to be 2 significant figures there? I can get rid of those zeros in front simply by changing the units. So that's something to be careful of. Zeros in front don't count because you can change the units and then the zeros are gone, okay? So it's a really important point to really hammer in. Zeros in front don't count. Zeros after count, okay? All right, and finally, we have an example here where we have zeros after. However, it is a little bit ambiguous. Do we mean 80.0 kilometers? Do we mean 80 kilometers? Do we mean it's about 80 kilometers? We're not really sure if it's 80 or if it's 81 or 2 because we couldn't measure with a resolution of 1 or 2, right? So this number here, as presented, 80 kilometers, is ambiguous. It could have 1 or 2 significant figures. If it has 3, it should be written, but won't always be written, as 80.0 kilometers, right? Now, there is a caveat here to this statement, and that is that every pure number has infinite number of significant figures. If I just state the number 1, and 1 is not a measurement of something, it's just a number, well, 1 is exactly 1. And so 1 has an infinite number of significant figures, right? So 1.000000 on to infinity. It's still just 1. So that's the caveat there to this 80 kilometers here. We might mean exactly 80 kilometers. So it's really ambiguous if you don't put a decimal there. Now, there's a little trick that you can do that's not included here in the slides, and maybe I should add later, is oftentimes when we're really being careful, we'll put 80 and then we'll put the decimal, but we will not put a 0 after the decimal. So it would read 80 point and then nothing, and then it would say kilometers. So 80 and then a dot and then kilometers. That would mean I definitely know it's 80 kilometers to 2 significant figures. The decimal really helps to identify how many significant figures there are, okay? So always pay attention to where those decimals are. Okay, any questions about that? I know I messed up the explanation the first time. That can usually hurt students. So go ahead and ask me if you do have a question about that. Give me a thumbs up if you're okay. Let me know you guys are here and you're okay. Couple people. Chiana, are you okay? Is that how you say your name? Is it Kiana or Chiana or? It looks like everybody.
Right, Professor. Kiana.
Kiana, okay, got it. All right, so let's go ahead and move on then. All right, so we have some rules here for calculations. It looks like I made a little mistake there with my animations there, but the rules for calculations are pretty straightforward. A lot of people get caught up on these rules. I honestly feel like teachers are just being a little bit too hard on significant figures sometimes, especially chemistry teachers. They're a little bit too strict on significant figures. You know, when you're first learning stuff, yeah, it's important to learn it the right way, but essentially when you're doing calculations with numbers, just make sure your result has the lowest number of significant figures of all the measurements that you used in your calculations. So multiplication, division, the result should have the least significant figures of the number that you used in the calculation. So you multiply, let's say, a couple numbers with 3 significant figures, and then you multiply all of those numbers by a number that has 2 significant figures, then your result should have 2 significant figures, okay? Addition and subtraction, well, you're adding up all these numbers, right? And if one of those numbers only has, for addition and subtraction, it's a little bit more complicated because you could have decimal numbers, like small numbers that have 2 significant figures, but you have a really large number and it has like 5 significant figures. But when you add those 2 numbers, your new number is going to still be 5 digits long, right? I don't have an example of that right here in the slides. Like I said, I didn't have a chance to really complete these slides, but it becomes something where you have to look at a case-by-case basis when you're adding and subtracting numbers. It should become obvious where to cut off your significant figures when you're adding and subtracting. Let me just come up with just a verbal example here. If I measure 10 kilometers and then I want to add on to that the length of a car, and the length of that car is 0.007 kilometers, right? If I add those 2 numbers, right, 10 kilometers is going to dominate any calculation that I do, right? If I were to add those 2 numbers, the answer is basically 10 kilometers, right? That's going to be a 2 significant figure result, even though I had, some number in there which was really accurate and small, right? So pay careful attention to those kinds of things. When you're adding and subtracting, it should appear obvious what where you should cut off your final answer and say, okay, I can only really say this many numbers here are reliable. Okay. So for example, with multiplication here, right, we have a 3 significant figure number times a 2 significant figure number. You're going to be a 2 significant figure answer there. Okay, and so I've written it out for you. A lot of people like to abbreviate significant figures as sig figs or SF for short, right? So 3 significant figure times a 2 significant figure is a 2 significant figure. Mastering physics will often tell you the answer, okay? It will tell you, give your answer to 3 significant figures or give your answer to 2 significant figures, right? So just make sure that you read the questions carefully. And if it says that, just do what they want you to do. Keep everything always exact whenever you do calculations, okay? Whenever you do calculations, always keep all of that information and always calculate with as many decimal places as you possibly can, because numbers can carry over, right? And they can, numbers that are not in significant slots can often multiply other numbers and carry the one, right? Multiplication, right? Carry the one over into a column where there is a significant figure. And so always use very precise calculations and only round at the very end when you present your result, okay? And mastering physics usually is pretty good about helping you with this, okay? Units and the SI unit system. We have some quantities on the left and the corresponding SI unit on the right, right? So length, time, and mass are 3 things that we can measure. And on the right are 3 units that we assign to those measurements. And that's pretty much how it goes. We have length, time, and mass, and we assign, in other words, we invent a unit system. We call that system that's in practice all around the globe the International System of Units, or Système International in French. That's why it's SI. We established that scientific system of units that is used around the globe. So learning this system of units, you can go to Europe, you can go to Asia, you can go to Australia, and you will be able to communicate with scientists and they will understand what you mean when you say meter or kilogram or second, right? I think it's pretty obvious everybody uses the same units of time all around the world, right? But I'll give you an example. In the American or the English system of units, mass is not measured by kilograms, it's measured by slugs. And obviously we know meters are SI, but length is measured by feet and inches, right? And miles in the English system or the American system, whatever you want to call it. And so it's important that we get our units straight, right? We want to make sure that we work with the right units. I'll just give you a quick bit of a story here. There once was a NASA project where NASA was working with scientists overseas, and there was confusion related to the units, and it resulted in I want to say it was $2 million worth of wasted resources, because they built this thing to spec, assuming the units were of a certain system when they got the data from people overseas, and it wasn't in their same system of units. And so boom, you get hit with this $2 million cash sink, right? And that's a real big bummer, right? That's taxpayer dollars right there. So it's very important that we have this system that everyone is using all around the world, the same system of units, right? And communicating, hey, look at me, I'm using the same system of units as you. Just want to double check with you that you're using this system of units, right? So that's my spiel on the units there. In this class, since everything is being done in Mastering Physics, double check when you go to submit your answer that you have the same units as the answer that they want you to have, right? They might want you to put it in units of centimeters, but you calculated it in meters. Double check that, right? Always double check that. Double check. Do they want it in centimeters? Do they want it in meters? Do they want it in kilometers? Because when you're calculating, you might write down this big number and you want to make that number shorter, right? You want to use scientific notation to shorten that number down a little bit. And so you put it in a certain, you might put it in kilometers, for example, but they want that answer in meters. Okay, so be aware of that. Here's some useful prefixes that are in the slide here. We're only going to go over these ones on the left, but on the right there, you see this big table with all kinds of prefixes, all the way up to 10 to the power of 24, and all the way down to the power of 10 to the minus 24. Absolutely insane. In the scale, on the scale of the size of the universe, you might see power 10 to the 24. Okay, for example, or actually even I'll give you a planetary example here on Earth. The mass of the Earth is roughly 6 times 10 to the 24 kilograms. Okay, so there you go. You could put it as a capital YG. Or excuse me, actually, you have to account for kilograms there as well. So my bad, actually, if you want to put that sucker in grams, that would be 10 to the 27, as a matter of fact. So that, you see, the numbers can get real big. When you talk on the size of galaxies, like masses of galaxies, things like that, it can get real big. Distances across the universe, the size of the universe, in other words, the radius of the visible known universe that we have observed with our eyes using telescopes, I believe is 96 billion light years. Okay, 96 billion light years. The age of the universe, according to the most recent accepted value, is 13.67 billion years. Okay. We can talk a little bit about that. It's not an appropriate topic for this course to really get into the measurements and all of that, but it is something that we can talk about, right? If you guys really want to take a little bit of time to talk about that kind of stuff. But I would need to do a little bit of prep on my side to actually be able to give a little bit of a lecture on that. So we're talking big. Sometimes we're talking real big. So we need these really big prefixes, but we don't always use them that much. On the small side, we'll come across nano. We'll come across pico, especially in the second semester. For example, Newton's big G, the big G constant, the gravitational constant, known as the universal gravitational constant. That thing is like 6 times 10 to the negative 11, with some units, obviously. So that's real small. Nanometers, and one that's not listed here is the angstrom. Angstrom is not really a prefix, but it's a unit, which is 10 to the negative 10. Those are like the scales that we're dealing with when we talk about the sizes of atoms. Okay. Over here on the left, though, we have the most useful guys for this class. Okay. That's going to be kilo with a subscript K, or sorry, not a subscript, but an abbreviated prefix K. That has the value of 10 to the third, or in other words, 1,000. Kilo means 1,000, right? 1,000 meters is 1 kilometer. Centi, which is 10 to the negative 2, comes up a lot. It's not that frequent, though. We try to use milli. We try to use just the powers of 10, which have a multiple of 3 in the exponent. So 3, 6, 9, negative 3, negative 6, negative 9. So centi, 10 to the negative 2, it means 1/100th, right? Century, right, is 100, right? That would be 10 to the 2. And then we have milli, 10 to the negative 3. We're all familiar with millimeters, hopefully. 1/1000th of a meter. So if you get a millimeter stick, right, and you look at that, those little small markings on there are millimeters. That's enough about that, okay? If there's any questions about that, let me know. Here are some examples of other units that we might come across in this class. And I just want to touch bases with you guys on these kind of units, because we do use composite units all the time. And so it's important to kind of familiarize yourself with them before they come up, so that way you're not really focused on that. You're more focused on the actual physics, right? So for length, we use meter, lowercase m. Time, we use second, lowercase s. It is not SEC. Seconds is abbreviated with a lowercase s, not SEC. Okay, so just a little point. Some people put SEC. It's not that big of a deal, but if you want to be official, just use a lowercase s. Mass, kilogram, kg, right? So that's, you normally would see maybe grams with a, but we use kilograms for mass in the SI system, okay? It comes built in with that prefix of K. The reason for that is because kilograms is a lot more human sized than gram, right? A person might be anywhere from 40 to 60 kilograms. Well, maybe that would be like a younger person actually. So maybe anywhere from like 50 to 80 kilograms, something like that, will be like the mass of a person, for example. Like a book, like the book I showed you guys earlier, that'd be like a kilogram or 2 kilograms, something like that. It's a very human unit, very human oriented unit, the kilogram. Electric current, we use amperes. That's a capital A. That won't come up until the second semester. Temperature, Kelvin, capital K. This will come up. This will come up this semester, unit of temperature. An amount of a substance, we will use this semester, I believe, around the time we talk about temperature and things. The mole, that's a unit you use all the time in chemistry, right? It's counting. It's abbreviated MOL. Sometimes you do see things like kilomoles or millimoles. Those do come up. Not very often, but they do. Luminous intensity. This is the brightness per square meter of a light. Very useful, actually. This is how you kind of plan out if you're going to buy a monitor for your computer, right? You want to look at this luminous intensity unit, and you can really see, okay, is this going to be like a bright screen? Is it going to have good colors and things like that? And there's other measures for like contrast ratios and things like that. This particular unit may or may not come up this semester. Okay, we'll leave that up to chance. We'll only use some of these this semester, okay? But these composite units, though, can often be written in terms of length, time, and mass, okay? That's the end of what I have here in my slides that I was working on. Unfortunately, I ran out of time. We'll go ahead and switch over here to, We'll go ahead and switch over here to the pre-built, the slides they send with you, and we'll take a look at some stuff here. We kind of just finished up on the units, okay? So now we're going to talk a little bit about converting units. So converting between units usually requires a conversion factor, okay? And sometimes that factor is simply due to a prefix that you're using. For example, here we talk about powers of 10, right? Converting between kilometers and meters, right? It's just a matter of multiplying or dividing by 1,000. Okay, so
Professor,
go
I'm
ahead.
not sure if we see your slides
Oh,
because we're
okay.
still on the previous ones.
Whoopsies. All right. Here we go. Excuse me. Okay. So like I was saying, converting units just simply requires a conversion factor. And oftentimes you can figure out what that factor is given some specific conversion factor for length or for time or for mass. And then you figure out how to convert an answer from one series or composite unit into another composite unit using multiple conversion factors. Okay, for example, 1 meter is 3.28084 feet. Okay, and an 8,611 meter mountain, that would be like Mount Everest, right? That's the tallest mountain, and I think that's what's in the picture here, is 28,251 feet high. Now, there are probably some people who disagree with that exact measurement of Mount Everest, but that's the idea there, is that we can convert between these two different units. 1 meter, I don't like to remember this number here, 3.28084 feet. I like to remember that 1 inch is exactly 2.54 centimeters. And you might be wondering, well, what do I mean by 1 inch is exactly 2.54 centimeters? What I mean is that 2.54 centimeters is not 3 significant figures. but it is an exact number. It is 2.54000000 all the way infinite zeros after that 4. That is an exact number. Okay. And I believe this 3.28084 is also an exact factor there. All unit conversions should always be exact. Okay. They should always be exact because you don't want to accidentally change the actual measurement that you made. If it wasn't exact, you would artificially be inserting some uncertainty into your measurement, and that is not something that we'd want to do, right? Okay, so well, maybe a couple more comments here about converting. So I'll just give you a couple examples. For example, 1 hour is 60 minutes, right? 1 minute is 60 seconds. So we can figure out quick little head math. That 1 hour is 3,600 seconds, right? That's 60 times 60, right? We have 60 seconds for every minute, and we have 60 minutes. So 60 times 60 is 3,600, right? 6 times 6 is 36, right? And we have 2 zeros there, add them on in the end. That's how I did that in the head, okay? So we can come up with factors like that for all kinds of things that we already know. 24 hours in 1 day, right? 365.25 days in 1 year, etc., etc. For kilograms to pounds, it's about 2.2 roughly. That's not an exact value. So we'll introduce conversion factors as we need to, like as we come across topics and there's an English system, an English unit that we're more familiar with, for example, pounds. In this class, we will use newtons for force. That's the SI unit, but pounds is also a unit of force. And so I'll give you like a conversion factor for that, just to kind of wrap your mind around, okay, how does this relate to pounds? Like how big is this force? How much is this pushing force? That kind of thing. Okay. Any questions about that? Hopefully the tutorials are doing a good job of walking you through some of these some of these unit conversions, because I don't think there's going to be any great examples here in these slides. So just if you need help with any of that, make sure you contact me soon before it becomes too late and you're feeling like you're behind. Order of magnitude and rapid estimation. Okay, here we have a little scenario where we're looking at the top of a building and we're trying to figure out, well, how tall is that building, right? It's a 5-story building, but not all 5-story buildings are created equal, right? Okay, there's a little signpost here for the bus, and we know that's about 3 meters. It's a lot easier to approximate the height of something that you can walk up next to, right, and kind of use an arm's length to kind of reach above you and say, oh, okay, yeah, that's about 3 meters, right? That's pretty easy. You might know that you're 1.5 meters tall. You can take your height in feet and convert that. A lot of countries will actually talk about how tall they are in centimeters. For example, I believe I'm like 190 or 191 centimeters tall. You guys can't see me, but that's pretty tall. It's like 6 feet 3 inches. I know, like, for example, in Asian countries, they talk like that. It's like a 3-digit number for how tall you are. And that might also be the case in some European countries too. So we can kind of look at a triangle here, right? In the bottom, we just kind of draw up a triangle for ourselves and kind of approximate. Well, I'm 1.5 meters, but it's a lot easier to work with 2 than it is a 1.5, right? And, I can approximate the distance. Oh, whoops, sorry. I can approximate my distance from where I'm standing to the building simply by walking, right? And I can walk over there and I can say, okay, it's about, maybe 20 paces, something like that. And for each pace, each step I take is about 1 meter. And so I get about 18 meters. Well, okay, 18, that's kind of a hard number for me to multiply in my head, right? So let's call that 20. And then that'll be easier for me to calculate with, right? We're really just talking about approximation, not exact calculation, right? Approximate the answer. And it's very useful because it can help you understand, is the answer I got for my actual calculation? Does that make sense? Or is this just wildly off? Did I make some mistake somewhere and my answer is like 100 times bigger than the answer should be? And that's where this idea of rapid estimating comes from. Do a quick little head calculation. Does this answer make sense? Can I like, okay, this is a 20, this is a 10, this is a 100. Do your little calculation, get your answer right. Okay, this answer, yeah, this answer is pretty close to what I got. So I can trust my calculation, right? But if your answer is way off, you can say, whoa, okay, let me go take a look at this again because I definitely got the wrong answer, right? And so they have a little spiel here about this. So a quick way to estimate a calculated quantity is to round off all numbers to one significant figure and then calculate. Your result should at least be the right order of magnitude. This can be expressed by rounding it off to the nearest power of 10. Right? So that's the idea. Diagrams can also be useful, obviously, right? And on your guys' homework problems, I always try to make sure that there's good figures for all of the problems. So let me know if you get a question that doesn't have a figure and it's unclear about what you're being asked to do, and I can help clarify. Dimensions and dimensional analysis. Well, we kind of already talked a little bit about this. Dimensions, length, time, and mass. Those are dimensions. Meter, second, and kilogram, those are units. Those are not dimensions. Those are units that we assign to dimensions. Okay. And so we perform dimensional analysis calculations sometimes to kind of foreshadow what an answer should look like or what a formula should look like when we go through and actually derive that formula from scratch. We can ask ourselves, well, if we combine length, mass, and time in a certain way, we'll get a certain unit. And that unit is what we're after. And that tells us, okay, if we have a quantity like velocity, well, velocity is length over time, right? Acceleration is length over time squared. Displacement is length, right? Mass is, mass is mass. And so you can combine those dimensions of length, time, and mass in such a way to get the dimensions of the quantity you're after. And that clues you in as to how you should multiply the velocity, the acceleration, and the mass, and those quantities together to get the units that you want. It's kind of like a guess and check type of process. It helps you understand where you're going, what your formula should look like. If you derive a formula and then you look at the units, or rather the dimensions of that formula, and you see, wait a minute, this doesn't add up. I know it should be these dimensions. Well, then you must have made a mistake in your derivation, right? And so you can go back and check that and make sure that you correct that mistake and get the correct answer for that, okay? So here they give an example, as an example, speed, which has the same units as velocity. Distance over time, or I've been using length over time, which is the same. Distance and length are slightly different meanings in physics, but they both represent that length dimension. Okay. And then actually there it says it right below the distance over time. It says L over T, that capital L meaning length, capital T meaning time. Quantities that are being added or subtracted must always have the same dimensions, okay? In addition, a quantity calculated as the solution to a problem should have the correct dimensions. So if you go through your calculation and you're canceling out your units to make sure that you have the right units for your final answer, but you find out, oh, wait a minute, I messed up. Those units don't match up. I should have got length, but I got length squared divided by time. Well, then you definitely know you made a mistake somewhere, right? So almost done with this stuff. Here's the summary here. Theories are created to explain observations and then tested based on their predictions. Dimensional analysis is useful for checking calculations. This is just a little summary here. We already know what's going on. It's going to be recorded and posted. So let's go ahead now and switch over to the chapter 2 stuff, because I just really want to get you guys something for this stuff, right? So you don't feel so lost here with everything happening at the beginning of the semester. So can you guys see the chapter 2 now? Give me a thumbs up or something. Okay, I see a couple thumbs ups there. So yeah, see, this is just like an official thing. Don't copy it and send it out to students or something like that. Describing motion kinematics in one dimension. So I don't know the order of these slides. I really haven't had a chance to go through them ahead of time, so just bear with me here. The contents of chapter 2 here, we'll talk about frames of reference, displacement, average velocity, instantaneous velocity, acceleration, motion with constant acceleration, and just some general problem solving with those quantities. And we'll take a look at freely falling objects. It turns out freely falling objects are objects in motion with constant acceleration. So that's really nice. That simplifies a lot of stuff. And then some graphical analysis of linear motion, which is actually a really important skill to have. Okay, so here we go. Let's get into it. Reference frames and displacement. Any measurement of position, distance, or speed must be made with respect to a reference frame. For example, if you are sitting on a train and someone walks down the aisle, the speed with respect to the train is a few miles per hour, right? If somebody's just walking at a brisk pace, a brisk walk down the train, right? They're just walking. That's like a couple miles per hour. However, their speed with respect to the ground is much higher, right? The train is moving. Maybe it's a bullet train. It's going 100 miles per hour. And they're walking, let's say 2 miles per hour on that train. Well, then with respect to someone who is outside of that train and just standing at the train station, they would see that person pass by them at 102 miles per hour, right? You would add up those two velocities to get the velocity relative to the person at the station, okay? So that should be a fairly simple statement. Add up velocity, relative velocities to get a new relative velocity with respect to another reference frame. All measurements are made with respect to a reference frame. For example, everything we do in lab is are measured with respect to the earth as a reference frame. Or in other words, to the ground. Okay, so we need to make a distinction between distance and displacement. Displacement is the blue line in the diagram here at the bottom right. Displacement is a vector, okay? And that's why it is drawn as a vector in the diagram. It is a blue arrow which has a beginning and an end, okay? And the displacement is the difference between your initial starting position and your final or your ending position. You take the final minus the initial. That gives you the displacement, okay? And distance traveled can obviously be different than displacement, right? For example, if you walk 70 meters down the street and then and you walk that 70 meters away from your house, but then you say, oh, wait a minute, I forgot my phone, and you turn around and you walk 30 meters back, well, then you've traveled 100 meters, but your displacement from your home is 40 meters, okay? And then you may realize, oh, wait a minute, I put my phone in my back pocket, and then you stop for a second while you pull out your phone, right? And so your displacement is 40 meters, but your distance traveled is 100 meters. You can also have 100 meters distance traveled and 0 meters displacement. You go to the store, and then you come back home. You traveled 100 meters. It was just right down the side on the block, and you just came home. Well, you're home again. Your final position is the same as your initial position, and so your displacement is 0. So we write displacement as a difference between two positions, and usually we'll say final minus initial when we say it out loud. Here we've listed it as 2 minus 1, which is also okay. On the left diagram here, we have that the displacement is positive because, again, we're doing motion in one dimension, and so the displacement is along the positive x-axis. So we can use a positive number to describe that vector. A positive number means along the positive axis for a one-dimensional vector. Now, displacement can also be negative. In the right diagram, we have a negative displacement. All that means is that your position changed to the left instead of to the right. So the vector now points to the left because it is a negative value. Vectors are also 2- and 3-dimensional objects, in which case a single number is not enough to describe the vector. You'll need two numbers in 2 dimensions or 3 numbers in 3 dimensions, and all of those numbers could be positive or negative, and that will tell you the direction that the vector is pointing in. Okay, we'll definitely not do much with 3-dimensional vectors. Maybe we'll do a little bit of stuff in 3 dimensions in the second semester, but in this semester we'll stick to 1 dimension for now and 2 dimensions in the next chapter. Okay, average velocity is a very important topic in this class. Velocity in general is very important. Velocity is the quantity that we like to use in physics. That's what everything is built on. But we're often most familiar with the idea of speed, how fast something is moving, right? Velocity also is how fast something is moving, but it includes a direction that that object is moving in. So velocity is a vector. Now, average velocity just means it's the average vector, right, for the velocity, okay? But what is speed? We're more familiar with speed, okay? How far an object travels in a given time interval is what speed is. It is distance traveled divided by the time it took to travel that distance, or the time elapsed, okay? That's average speed, not instantaneous speed. It is also possible to calculate an instantaneous speed. It's not something that we usually discuss very often because instantaneous velocity is far better than instantaneous speed, right? If we have that direction information, that helps us even more in knowing what's going on in a problem. Notice though that average velocity is a vector, and therefore it must be based on displacement and not distance traveled, okay? Distance traveled is not a vector, it's what we call a scalar, or in other words, just a number. Displacement is a vector, and therefore we define the velocity using the displacement so that the velocity is also a vector. Again, this idea of vectors is really important. So average velocity is simply the displacement divided by the time elapsed, okay? We can write that out a little bit more. We can say that's the final position minus the initial position, which is consequently what the displacement is. And then we divide that subtraction by the time elapsed, and that gives us the average velocity, okay? For instantaneous velocity, we need to do a little bit of calculus. And so this is something that even students who have not had the calculus should also understand, this idea of instantaneous velocity. What it is essentially your velocity at a specific instant in time. And that is information that we can figure out without actually using calculus. We don't always need calculus to figure out the instantaneous velocity. But in general, if you have some crazy object that's kind of flying around and doing something crazy, right, very unpredictably, then you do need calculus to calculate the instantaneous velocity. Okay, so even those of you who are in the Physics 210 class, I will not expect you to calculate instantaneous velocity of some super complicated motion, okay? So don't worry too much about that. Oftentimes we can read instantaneous velocity off of a graph. We can plot velocity that we measure over time, let's say of a car driving down the road, or of a baseball, right? A pitcher throws a ball and we're measuring the velocity of that over the course of the ball's trajectory, and we can plot that. And so on the left side, we have a graph which is showing a constant velocity, right? Not only is this the average velocity at all times, it is also the instantaneous velocity at all times. That is because the velocity does not change with time. As you can see, we have a horizontal line there. It's a flat line, right? That means it's the same for all time. So it's 40 meters per, it looks like it's 40 kilometers per hour there. I just wanted to make sure I got the units right on that. I kind of tripped up for a second. The velocity is 40 kilometers per hour all the time. That means the average is 40, and that means the instantaneous at any time is 40, okay? Now moving on to the diagram on the right, we have the velocity is doing something much different. If we look at the origin of this plot, we see it says the velocity is 0, right? At time 0, the velocity is 0. But as we progress through time, it looks like at 0.1 hours, that first demarcation of the time there at the bottom, at 0.1 hours, the velocity is now at 50 kilometers per hour. So this gives me the impression of some sort of car driving, maybe you're driving to work or something, right? And then you have to slow down. You're going through a zone where the speed limit is lower. So at 0.2 hours, your speed has now dropped. You're decelerating, or in other words, you have a negative acceleration relative to the direction of motion. And so you're slowing down, right? And your velocity around 0.3 hours is now a steady 20 kilometers per hour. And then finally at 0.5 hours, or in other words, in 30 minutes, right? Little quick conversion in your head there. 1 hour is 60 minutes, right? Half of 60 is 30, right? So 0.5 hours, we're back at zero velocity again. So how do we interpret this motion? Well, one way to interpret it is to average out all of these velocities, which they've already done for us here in the plot. The average velocity is 30 kilometers per hour. It kind of makes sense, doesn't it? We're up at 50 kilometers per hour for a short stretch of time, and then we're down at 20 kilometers per hour for a little bit of a longer time, right? So when we average those two out, our average velocity will be a little bit closer to that 20 than it is to that 50, right? And so when we actually compute the average, we end up with 30 kilometers per hour. Now, one thing that you may have noticed, if you're really keen on these kinds of things, you're really good at reading these plots, you'll notice that the velocity is always positive. What does that mean? Ask yourself that question. What does that mean that the velocity is always positive? Give you a couple seconds to think about that. Okay, now here's the answer. What it means is that velocity, if you can see me, is pointing only in one direction, in the positive x direction. And so you're always moving away from where you started, okay? So this is kind of like you're going to work and you arrive at work. You park in the parking lot and you go into work. So there's no turning around. If you were to turn around, your velocity would become negative because you're moving in the opposite direction. So this is velocity only in one direction. You never change and come back. If you were to look at a plot where you drove to work and then you came back home, what you would see is now you'd be looking at negative velocities on the next part of the graph. And then you would, again, once you came home and parked your car, it would end up on 0 again, okay? Let me see, are there any questions? Any of the students who are still here? Any questions on that? Okay, so we'll keep going. So acceleration, what is acceleration then? Acceleration is often a hard concept to understand if you really have a limited knowledge of physics. A lot of times people mistake acceleration for how fast something is moving, right? But wait, how fast something is moving is speed or velocity, right? So acceleration, we give it another name, not to make things arbitrarily complicated, right? We give it another name because it really is a different value. It really is a different physical quantity, okay? So acceleration is the rate of change of velocity. In order to have acceleration, you have to have change in velocity. I'm going to do something I normally don't do. I'm going to go back to the previous slide. On the graph on the left side, the velocity never changes. What does that mean for the acceleration? Think about that for a second. Well, if the velocity doesn't change, then the acceleration must be 0 because the acceleration requires the velocity to change, okay? How about in the second graph? Is there an acceleration? Well, certainly there must be because the velocity is definitely changing, right? And so we have an acceleration there. So average acceleration is simply the change in velocity divided by the time elapsed, okay? Instantaneous acceleration That's a very complicated issue. We really need calculus to understand that. Even those of you who are in physics 210, I will not expect you to compute the instantaneous acceleration of a complicated system. However, all of you, including physics 205 and 210, should be able to read off, if I gave you a plot, if I gave you a graph like these two down here, which was acceleration versus time, surely you should be able to read the plot and tell me what the instantaneous acceleration is, because that's simply a matter of reading the plot, okay? So just to be clear on what I expect from you guys. Okay, and so just reiterate one more time, average acceleration is the change in velocity divided by the time elapsed. That means you can take your final velocity and subtract your initial velocity and then divide that by the amount of time in which that change occurred. And that will give you your average acceleration for that time period. Now on the top, we have a car which is accelerating, or sorry, in this entire diagram here, we have a car which is accelerating with an acceleration of 15 kilometers per hour per second, okay? Strange units to use for acceleration most often will use meters per second, so meters per second divided by seconds. Another way of saying that is meters per second squared. That can be a little bit confusing for newer students when they first encounter acceleration. So we'll try to write it as meters per second divided by seconds. At t1 equals 0 seconds, our velocity v1 is 0 meters per second, okay? But we have an acceleration. We are not moving, but we have an acceleration. Let that sink in for a second. That is a very important concept to understand in a physics class, such as this one. You can be not moving, in other words, your velocity is 0, but you still have an acceleration. That is because acceleration is the rate of change of the velocity. You may not have velocity now, but you will have velocity a second from now, right? If you have acceleration. Now, one thing that cannot happen is you cannot have 0 velocity and then you still have 0 velocity, you still have 0 velocity, you still have 0 velocity. That cannot happen. You cannot have 0 velocity for an extended period of time and have an acceleration. That is not possible. But it is possible to have an instantaneous velocity of 0 and not have an acceleration, okay? So as we can see, after 1 second, just 1 second, now we have a velocity of 15 kilometers per hour. That makes sense, doesn't it? The acceleration here is 15 kilometers per hour per second. So every 1 second, we would expect to gain 15 kilometers per hour to our velocity. And so after 2 seconds, we're at 2 times 15 kilometers per hour per second, right? And so 15 times 2 is 30. And then, of course, 5 seconds later, our velocity would be 75 kilometers per hour, okay? Any questions about that? Okay, let's go ahead and move forward. The acceleration is also a vector. Remember that velocity is a vector, and the acceleration is based on the velocity. And so therefore, acceleration must also be a vector, okay? The 3 important vector quantities are number 1, displacement, number 2, velocity, and number 3, acceleration. You should understand all 3 of those quantities are vectors and how to use them in solving problems as vectors. Quantities which are not vectors are 1, distance traveled, position, that would be number 2. Number 3, speed, okay? Those are not vectors. Those are what we call scalars, or in other words, just numbers. They don't have direction, okay? So the acceleration is a vector, although in one-dimensional motion, we only need the sign. We only need a plus sign or a minus sign, right? We only need to know, is it along the positive x-axis or is it along the negative x-axis? And so here's an example where we have positive velocity right? The velocity vector is pointing along the positive x-axis, 15.0 meters per second. How many significant figures is that 15.0 meters per second? Think about that for a second. How many significant figures is that 15.0 meters per second? Did you come up with 2 or did you get 3? Okay, the correct answer is 3. That 0.0 counts. We're saying it's definitely 15.0, so it's definitely 3 significant figures. Okay. So at t1 equals 0, initially, our initial time, that 0 has infinite significant figures. We have a velocity of 15 meters per second, but our acceleration is in the opposite direction. It's negative 2.0. How many significant figures is that number? Did you get 2? That's the correct answer. It's negative 2.0 meters per second squared. That's going opposite the velocity. Okay, what does that mean? Think about that for a second. It means that we're losing, or in other words, we're gaining in the negative direction 2 meters per second per second. In other words, we're slamming on the brakes. We're slowing down, right? Our acceleration is against our motion, our velocity. By the way, whenever you hear the word motion, always associate the word motion with velocity. The motion of an object is its velocity at that time. Okay, motion and velocity are synonymous. Now, if we want to talk about the trajectory, right? What's important for the trajectory of an object? You need to know the displacement, the velocity, and the acceleration, okay? So just a little terminology there for you. So when we slam on the brakes here, 15 meters per second, that better decrease, right? We have a negative acceleration. Our velocity is positive. We have a negative acceleration. So after 5 seconds, how much velocity are we going to lose? Well, we lose 2 meters per second every second. If we decelerate or accelerate in the negative direction for 5 seconds, well, then we're going to have 5 times negative 2 is negative 10. And we're going to add that to the velocity. So in other words, we're going to subtract 10, right? And so after 5 seconds, we have a velocity of 5 meters per second, okay? So run through those numbers yourself, actually write them down just to get that in the habit of writing it down and calculating that. That's a nice little example there. Now, one important thing to note is that in the case of a car, slamming on the brakes is obviously going to be a negative acceleration relative to your velocity, okay? However, there are many cases in which an object with a negative acceleration that has a positive velocity will eventually turn around and start moving in the opposite direction. For example, if I were to crumple up a piece of paper and throw it at a fan, then that fan would give that piece of that paper ball a negative acceleration, right? I would throw it with a velocity and it would move towards that fan with a positive velocity, but the fan is blowing against it, giving it a negative acceleration. Eventually that paper ball would stop moving towards the fan and start actually blowing away from the fan, right? And so that's an example of where the velocity is initially positive, but then it becomes negative because of the negative acceleration. So keep that in mind. When you see a car like this in a picture, it's easy to kind of trick yourself into thinking, okay, negative acceleration, my final velocity is going to be 0 eventually. That's not always the case. Again, think about throwing a paper ball at a fan, right? That fan is going to blow the ball back at you, right? It's giving that negative acceleration to that paper ball, and it's turning its velocity around. It's making the velocity go in the opposite direction, okay? All right, next slide. If there are no, I see a couple chats here, so let me address these. So I see a 0 question mark. I'm not sure. Can you clarify where you wanted to ask that question? I'm sorry, I didn't catch it earlier. And then 3, answering a question. Oh, so it was a private chat. Okay, that's fine. Yeah. So are there any questions now for me? Give me a thumbs up if you guys are okay. Sorry for keeping you guys so long. I know this is crazy to go to 10, 16. This is absolutely insane, and we'll never do this again, I promise. Okay, so we're all good. All right, so let's go ahead and move on to the next slide. Just this again, sorry. So there is a difference between negative acceleration and deceleration, okay? Deceleration is kind of what you do in a car. You slam on the brakes and you decelerate, right? And your velocity, the magnitude of your velocity decreases, okay? And eventually reaches zero. That's different than a negative acceleration. Your velocity can increase if you have a negative acceleration. For the example with the paper ball, right? I throw the paper ball at the fan and I throw it kind of slow. And when the fan blows it back at me, it blows it back at me faster than I actually threw it at the fan. Well, that's an example of the ball has a negative acceleration, but its velocity is actually getting bigger, so to speak, right? It's becoming a bigger negative number. In other words, the magnitude of the velocity, or in other words, the speed of that paper ball is getting bigger, right? And so negative acceleration is acceleration in the negative direction as defined by your frame of reference or your coordinate system. Deceleration occurs when the acceleration is opposite in the direction to the velocity. In other words, you're slowing down. And of course, I just gave you an example of where you can slow down and then your velocity changes directions. And then all of a sudden now you're speeding up, right? So really got to wrap your mind around that and really be careful about your signs. Okay. The instantaneous acceleration is the average acceleration in the limit as the time interval becomes infinitesimally short. Again, this is instantaneous acceleration. It is important to understand this, and it is important to understand instantaneous velocity. It means your velocity at a specific instant in time. Okay. Now, a little calculus knowledge for those, maybe some of you have taken calculus, right? I know some of you have, but that just means a limit as delta t approaches zero. Essentially, you pick a very small time interval in which delta t is very, very small, and you calculate the change in the velocity, which is going to be also very small for an object that's not moving too fast, right? And then divide that by another small number. And of course, you take a small number divided by a small number, and you're going to get, you could get a very large number, right? That's something that can happen, right? And so be very careful when you're working with instantaneous velocity or instantaneous acceleration. Instantaneous acceleration of something which is moving with constant acceleration. Obviously, the constant acceleration, that means average and instantaneous are the same thing. Okay, so always keep that in mind. Average acceleration and instantaneous acceleration are the same when the acceleration is constant. Okay. Now, the average velocity of a time interval, the average velocity of an object during a time interval is given by displacement divided by the time elapsed, right? Delta x over delta t. And so normally we'll write something along the lines of final minus initial if we're interested in specific times. But in general, you can write that the average velocity at any point in time is whatever your position is at that time minus your initial position divided by however much time you're measuring beyond the time instant, the time that you began your stopwatch, right? So for example, if you use a stopwatch, it starts at 0 and you push start, then you obviously whatever time is on your stopwatch, that's your T, right? But if you push that lap button, right, where it saves a time, right? Well, then that might be your initial time that you're interested in. And so then you would take the new time that you're reading off the stopwatch and subtract that time that you got when you push the lap button, right? And so you have a different delta T there, okay? Oftentimes we can just set our initial time to 0, right? And so on the far right over here, we see that we have an x minus x0 divided by just t. So we've decided t initial or t0 is equal to 0. And the acceleration, for constant acceleration, obviously it's the same as the average, but in general, the average acceleration is the velocity at some instant in time minus the initial velocity divided by the amount of time that's elapsed. So again, we've set the t0 portion to 0. And so we have v minus v0. A lot of times you'll see this, like maybe if you look at some sources online, you'll see v final minus v initial. But here we've decided, okay, any velocity minus whatever the initial velocity was divided by however much time has elapsed. That's the formula that we'll use for average acceleration. Okay. Now we can do a quick little derivation to come up with a nice little formula which describes how much distance is traveled, or rather how much displacement an object has, which is going to be the same as the distance if all the quantities are positive. But if some quantities are positive and some are negative, it will not be the same. So the displacement of an object with constant acceleration is given by this formula down here at the bottom. Now, I just wanted to talk over this just to let you guys just kind of take all the equations in here, but I will explain every step of this process here, okay? So the velocity is maybe increasing at a constant rate if you're accelerating, right? So if you're in motion with constant acceleration, then what that means is that your velocity would be increasing. Well, that means your average velocity would be increasing too, right? So what we do here in a situation like this is we take the idea that the displacement is going to be your initial displacement plus your average velocity times time, right? And we plug in this formula for the average velocity, okay? So in the very first equation there, 2-8, that is simply a statement of average velocity doing a simple numerical calculation. I have one velocity here, I add it to this other velocity, and then I divide by 2. I used 2 different velocities, and I just divided them by 2 to get the average, okay? That's what kind of average that is. Now, in the next equation there, below the 2-8, we are saying the displacement is equal to our initial position plus how far we've traveled due to our velocity. Velocity times time is an amount of displacement that you've traveled in a certain time period, okay? And so we make sense of that equation in that sense that we have displacement, we begin at an initial position and then we travel some distance, and that's our new position or our new displacement. And we can take that 2-8 formula and plug it straight in to this expression for x. When we do that, we have to distribute the factors here. We have to multiply through by the t, right? And in doing so, we have multiple velocity terms with t's associated with those. And so it's not shown here. I encourage you to write it out yourself. You should have an x0 plus a v0 divided by 2 times t, and then you should have a plus v divided by 2 times t, right? But of course, we just took a look at v. I'm going to back up again. We just took a look at what v was, right? We can write v, oh, sorry, it's right here. It's the last expression here. We can rewrite v in terms of a. We can take a and multiply by t, okay? And then we can add v0. So we take a, we multiply by t, we add v0. Well, that cancels all the stuff on the right side except for v. So we should have v0 plus at equals v. We're going to take that equation, write that down. I'll read it out one more time since I don't have it here on the slide. A times t plus v0 equals v. We're going to take that equation and we're going to plug it in to the line 2 on our derivation here. Plug that equation in, at plus v0 equals v, in for v in the second line. When you do that, the third line is what you get. You get v0 plus the formula you're plugging in, which is v0 plus at. You still have that factor 1/2 there, and you still have the factor of t all the way on the outside. Distribute that t, okay? Distribute that t, you have two v zeros. Write it as 2v0. It's going to cancel with the factor of 2 in the denominator, but you're still going to have a factor of 2 dividing the acceleration. Okay, so that's why we have that 1/2 at squared there in the final answer. I know this is a crazy, I really should write these steps out for you guys, but again, right, we're just trying to get through this. And in the future, I will have much nicer slides for you guys. Okay, so that's our equation there. So our new position or our new displacement here can be written down in terms of our initial velocity and our acceleration. Okay. And notice the acceleration has a factor of 1/2 and a factor of t squared. Suppose we set the initial velocity to 0. Okay. Suppose we set the initial position to 0. Okay. So we have x equals 0 plus 0. Okay, get rid of the zeros. X equals 1/2 at squared. That's a nice, useful formula. When your initial velocity is 0, oftentimes you can default to the formula x equals 1/2 at squared. That's how much distance you travel, or how much displacement, in this case they would be the same, that you travel. It's just 1/2 times the acceleration times the amount of time you accelerated for, okay, squared. And you can see that the units work out, but there's an extra factor of 1/2. So that's the part that you have to remember, is that factor of 1/2. So acceleration is meters per second squared. T is seconds. So it's going to be t squared is going to be second squared. So meters per second squared times second squared is going to give you meters. Okay. Any questions about that? Okay, let's keep going here. Here's another useful formula that we don't really want to derive just yet. We'll actually save this one for later. When we get to energy, we can derive this formula a little bit easier. But that's that your final velocity squared, or the velocity you're interested in squared, is equal to your initial velocity squared plus this factor that has to do with your acceleration and your displacement. Oftentimes you'll see this formula written as v squared equals v0 squared plus 2a times delta x. Delta, again, meaning that final minus initial. Again, we present this equation without derivation here. We'll derive it later in the course, I promise. Okay, so now we have all the equations we need to solve problems with constant acceleration. That's an important point too. This equation 2-10 assumes the acceleration is constant. Okay, otherwise you can't use that formula. We shouldn't come across that in this class though. So there are 4 formulas that are going to be useful for problem solving. I think we should end there in terms of the lecture. There are more problems here that you can, I'll flip through the slides, but I'm not going to cover them. We're going to end now, but I'll flip through the slides here, and I'll give just enough time so that you could pause the video and watch this for and kind of go through this yourself. And that should be good enough for you guys to really finish off these assignments. Again, I won't talk about freely falling objects. We'll deal with them more and more throughout the class. Essentially, when an object falls under the influence of gravity, it falls with constant acceleration. And the value of that acceleration is, or the magnitude of that acceleration without sign, is 9.8 meters per second squared. Okay. And objects that are in free fall like that, we typically assume there is no air resistance. If we include air resistance, we really got to bust out some heavy calculus. So we will not do any air resistance type stuff in this class. We may discuss it here and there and talk about, okay, what happens if there's air resistance? For example, some of you may know that skydivers, right? They're experiencing air resistance, right? And they fall down at kind of a nice, easy pace. And that's due to the parachute on their back kind of catching the air as they fall, right? And slowing them down significantly. Okay, and so we'll just keep going here. This is kind of what I alluded to already, is graphical analysis here. We can see a position versus time graph here. Whenever you have position versus time as a straight line, that means your velocity is going to be constant. because the slope of that line is actually your velocity, right? So take a look at that. If you have a more curvy line, then you may not be able to compute the slope um, of that region of graph that you're interested in, and so you need calculus for that. That's a calculus topic, computing the slope of a curve at a point. It's called tangent line, if you want to look into that. Okay, and that ends everything. So we will now end the recording, and I hope that was helpful. In the future, it will be much more controlled, much more prepared, and much, much, much shorter. And so hopefully you guys get some value out of this, and this helps you guys. Of course, always ask questions if you need to. Okay, so take it easy, signing out.